Welcome everybody for yet another Hydrogeophysics webinar sponsored by Society of Exploration Geophysicists. We are glad to have Dr. Mohammed Ahmed speaking for us today. He is an associate professor at the Texas A&M University. He received his bachelor's and master's in applied geophysics from Suez Canal University, Egypt, and then he came to the US and got his PhD in geosciences at the Western Michigan University. He employs integrated approaches combining geophysics, remote sensing, GIS, modeling, and so on to a diverse array of complex geological and environmental issues. Currently, his research focuses on monitoring groundwater resources in arid and coastal environments and quantifying land deformation resulting from excessive groundwater use. With 2 decades of research and teaching experience, he possesses an outstanding publication record and has received numerous grants and awards in the past. Before giving the platform to you, Mohammed, let me ask the audience that you, myself, Laurie, and a lot of other SCG members will be at the SAGIP conference next week. Please don't hesitate to reach out if you have any questions regarding the Hydrogeophysics subcommittee to any of us. We would love to see you in person, obviously. So that would be a great opportunity. If you're there, totally reach out, and I look forward to seeing you all. And if you have any questions regarding this talk, please use the Q&A box, not the chat box. If the Q&A box for some reason is not working, please raise your hand. There's the icon, raise your hand, and then we will unmute you and allow you to ask your question directly. Without further ado, Mohammed, please.
Sure. Thank you, Sina, for the introduction. I really appreciate the opportunity. Good morning, everyone. Good afternoon, good evening, based on where are you sitting right now. And thank you for joining me today while I'm presenting our ongoing research in which we investigate what factors, what geologic and hydrogeologic factors controlling geomorphology of our coastal systems. And mainly our focus is a barrier island system here in Texas. But first, I would like to acknowledge my co-authors, Ramadan Abdurrahim, a PhD student who's working with me here at Texas A&M University, Corpus Christi. The work that I'm presenting today is Ramadan's PhD, part of Ramadan's PhD work. And also, I would like to acknowledge Dr. Mark Everett at Texas A&M University, College Station. This is the outlines of my presentation. I will start with introduction. Then I'll talk about the study area, objectives, and how we achieved our objectives, and results. Then I'll wrap up with conclusion. And if we got some extra time, I'll probably talk about our geophysics test site here at Texas A&M University, Corpus Christi, since I think that's a little bit relevant. And I also wrap up with final acknowledgement. So if you're living in coastal areas, you are one of 30% of the world population living in those areas. In US, 40% of the population living in those coastal areas. This image here showing distribution of coastal counties around the US. Coastal areas are very crucial when it comes to economy. They contribute to tourism and recreation industry, shipping and trade, fishing, energy production, as well as real estate and property development. However, those areas are very prone to natural hazards, specifically tsunamis, earthquakes, flooding, high tides, and sea level rise. This image here shows the tracks of tropical storms and hurricanes over the past 25 years. And as you can see, there's like huge number of those tropical storms and hurricanes that affect the coastal areas here. This is another map generated by NOAA that shows how often a hurricane would happen within 50 miles from the coastal areas. And those numbers are shown in years. So number of years, the red numbers or orange numbers are kind of from 7 to 10 years of recurrence time for those types of hurricane. Speaking of hurricanes, if you're living in Texas, you must witnessed summer 2017 Hurricane Harvey. And this hurricane made landfall on coastal Texas here and it was resulted in a huge damage that was estimated at $155 billion, which makes it the second to Hurricane Katrina that happened in 2005, and estimated loss of almost $200 billion. Luckily, if you're living in coastal areas and you have what we call barrier island system, you are a little bit safe. Barrier islands are landform, offshore landform. That's mainly like sediments that are running very parallel to the mainland. Those are very narrow feature and long feature, again, runs parallel to the shoreline, and they act as a first defense line against hurricanes and storm from like in this case, from Gulf of Mexico, in this case, to the mainland in Texas area here. This image here shows the distribution of those barrier island systems along the US Atlantic coast and also Gulf of Mexico coast. Those systems cover a little bit over 3,700 kilometers in length and 6,800 square meter in area. Barrier islands play very, very significant roles when it comes to how those areas, how the coastal areas are affected by storm and hurricanes. So they actually control how the areas are affected by storm and hurricanes. Not only this, but also they control the island, the recovery after those types of events. This is a satellite image, shows the distribution of barrier island systems along the Texas Gulf Coast. And as you can see, this thin line here, this is barrier island systems here. And that covers the Texas Gulf Coast area. And those areas, or barrier island generally, control storm impact. They determine which area are most likely to experience overwash, and also they affect the coastal areas recovery from the storm and hurricanes. And to give you kind of, or put you in a little bit of perspective about the washover channel, this is a drone photo of a barrier island system that shows one of those washover channels. So think about this as being cut. This is a dune field here and a dune field, and being cut by this washover channel because of a hurricane. So this is how much damage that could happen to those systems by hurricanes and storms. If you have dune system that is of wide extent, high elevation and gentle slope, and alignment parallel to the shoreline and wave direction, you're more safe, or you're sitting in a more safer area compared to other areas. However, recent research just reveals that the dune morphology, the elevation and the extent of the dune, is mainly affected by the subsurface conditions. And in this presentation, I'm sharing with you what we found so far on how the subsurface geology and how the subsurface hydrogeology are affecting the dune morphology here in Padre Island in Texas. This is again a satellite image, shows Padre Island in Texas, and it's located Padre Island. This is a Padre Island here, a strip of land. This is Padre Island. It separates Gulf of Mexico from Laguna Madre, and it is the longest barrier island system in the world, with a length of 182 kilometers and a width that could reach up to 3 kilometers. Sediments of Barrier Island, of Padre Island specifically, are very young. They're ranging in age from 4,500 to 5,000 years. This image shows elevation of Padre Island. It's color-coded digital elevation model, or DM. Red areas or red colors or yellow colors are higher elevation, and green areas are lower elevation. Generally, the average elevation of the island is very low. It's average elevation of 0.38 meters, but there are some areas that could reach, very anomalous areas that could reach elevation of 10 or even 16 meters. Shore face sediments, shore face sand and washover sand and alluvial deposits over Padre Island are sitting over what we call Pleistocene mud surface. And the depth to the mud surface in the island is ranging between 10 to 20 meters, and it has special variability. When it comes to geomorphologic features of the island, this sketch here shows those features going from the Gulf of Mexico to the east and Laguna Madre to the west. And this down image here shows the elevation, again, color-coded elevation. Red and yellow color are higher elevation, and green colors are lower elevation. So the first geomorphologic zone is the beach zone. And this is a zone that you can see here at the beach. If you visiting the beach, this is a beach zone. And this is, in this case, this is the closest portion or closest zone to the Gulf of Mexico. Then from the beach zone, you have what we call foredune. And this is a higher elevation area that contains a dune field. Then you have the second zone, third zone, which is the central part of the island, is called ridge and swell, or vegetated barrier flats. Then after this, you have back dune field. This is a back dune field, and ending up with a wind tidal flat, which is close to Laguna Madre. And so those are the four main topographic zones that stretch over the Badr Island. And the main objective of this presentation is to see how the morphology or elevation of those zones is controlled by the subsurface condition of the island. So our first objective is to investigate the mechanistic relationship between subsurface condition, mainly geologic condition and hydrogeologic conditions, and surface morphology of the island. We're mainly focusing on investigating subsurface electric conductivity, that is function of the lithology and fluid content of the subsurface. And also we started to examine the lateral and vertical extent of the freshwater lens in the island and see how those two features are correlating with the morphology of the island. The second objective is to see how this correlation vary from developed areas. This part of the island is developed areas where you have housing and development, and compared to undeveloped area, which is the pristine area here in southern part of the study area, if you will. So we did this exercise over the developed areas and also over the pristine areas. And we use the pristine areas or undeveloped areas as a baseline, if you will, and compare this baseline to the other developed areas. When it comes to geophysical techniques that we used, were restricted since Badr Island is part of the Badr Island National Seashore. So they restrict us when it comes to what techniques we used. We ended up using only non-invasive techniques. So we used as a frequency domain electromagnetic and the time domain electromagnetic. For the frequency domain electromagnetic, we mainly use the Geonyx EM31 system. It's mainly transmitter and receiver separated by a constant distance of 3.66 meters. And the transmitter is emitting primary field at constant frequency, 9.8 hertz. And the primary magnetic field, when it interacts with conductive materials, it generates secondary fields that could be sensed by the receiver. And based on the relation between secondary and primary field, you could solve for electroconductivity. And this is the electroconductivity profile in millisiemens per meter generated from this this tool. Just keep in mind that EM31 depth of investigation is very limited, is ranging between 5 to 6 meters at the most. This image shows the distribution of the EM31 profiles that we've collected. We've collected mainly 9 profiles. 8 of those profiles were distributed perpendicular to the shoreline, and one of them is parallel to the shoreline. Some of those profiles were collected in developed areas. Those are profiles that are collected in developed areas, profile 3 and 4 and 5 and 6 and 7. And some of them are collected in the pristine areas of the island, which is profile 8 here. So think of a profile 8 as our reference when it comes to comparing pristine areas to developed areas. Those profiles extend over a length that goes a little bit over 500 meters to over 1,200 meters. And they have very good coverage when it comes to data points per meter. We have almost 11 measurements per meter. So we have good coverage when it comes to the EM31 measurements. For the time domain electromagnetic, this has been covered by the previous webinars in very much detail, so I'm not stopping here much. But we used 10 meter by 10 meter loop as a receiver, and as a transmitter, and our receiver was used in sling-gram mode, where our receiver was outside the transmitter lobe, and with depths of penetration for this, we're getting up to like from 20 to 25 meters in this study. This map here shows the distribution of the 77 TIM stations that we've collected. Those stations were collected along, again, 13 profiles. Those are the same profiles that with extra profiles, but same location where we've collected the frequency domain electromagnetic. Some of those profiles are covering mainly the developed areas, and some of them are covering the undeveloped areas. And most importantly, some of those profiles are covering the entire island from the Gulf to the Laguna here. So we have this profile covering the entire island from the Gulf to the Laguna, and we have profile 11, which is we're displaying here, covering again the entire island from the Gulf and Laguna. And again, some of those profiles are mainly in the developed areas. Last database that we've collected is a topography. We use differential GPS system, Trimble GPS system to collect topographic information, mainly the elevation at each location where we've collected geophysical measurements. And we've correlated those measurements with a digital elevation model that recently acquired by USGS in 2018. And we found a good correlation between them. This is a digital elevation model of the study area, of the areas that we're focusing on. And again, warm color here are like higher elevation, and cold colors are lower elevation. So we've correlated our Trimble elevations with those elevation, and we find good relationship between them. And that's why we decided to use this DM, since it has a better spatial resolution of 1 meter. So we used our elevation mainly were generated from this DM. Now, our results, I will start first with showing the results for the frequency domain EM system. Then I will follow up with time domain, then I wrap up with connection between them. This image here shows the distribution of the profile. And those profiles are color-coded based on the conductivity. So warm colors are areas that has higher conductivity, higher electric conductivity, that could reach up to 400 millisiemens per meter. And cold colors or blue colors are areas with lower conductivity. And those conductivity could be as low as 7 millisiemens per meter. And as you can see, there is spatial variability in conductivity along the same profile. You go from the Gulf side to the Laguna side. Not only this, but also you've seen spatial variability in the conductivity from the northern part of the island, or if you will, from the developed areas to undeveloped areas. So, and in the next few slides, what I'm trying to do is I'm walking you through each of those profiles and trying to explain why we're seeing what you're seeing when it comes to the relationship between the elevation and the conductivity. But before doing this, I would like first to introduce the fact that we divided the island laterally to 4 main zones. And our distinction here were the break point in the conductivity. We use the break point in the conductivity and the elevation to define the island to 4 main zones. And those zones were correlated with the geomorphologic zone. So zone 1 is the beach zone here, and this zone cover a length from the Gulf to the four dune, cover a length of 40 meters. Okay. Then zone 2, which is 4 dune zone, and this zone cover a average length of 220 meters. Then zone 3, which is a central part of the island. First, think about this as a first part of the ridge and swell zone here. And zone 3 covering a length of 335 meters. Then zone 4, which is kind of think about this as a second half of the central part of the island. Okay, second half of the central part of the island. And this zone is covering 285 meters in length. Keep in mind that for this exercise, we haven't covered the back dune. Okay, so we haven't covered, we haven't collected EM profile that covers from the Gulf all the way to the Laguna Mar. Now, what we found is we found inverse relationship between conductivity and elevation. With higher elevation, we're getting lower conductivity, and with lower elevation, was getting higher conductivity. The correlation coefficient between those two parameters were calculated to be 0.7, very significant inverse relationship between two. And what I'm showing you in this slide next is I'm giving you kind of a big picture when it comes to elevation and conductivity of each zone. So zone 1, which is a beach zone here, has the lower elevation with average elevation of 1.4 meter and the highest conductivity of 290 millisiemens per meter. Following this zone is zone 2, which is the 4 dune zone. And this zone is the one of the highest elevation, average elevation of 4.5 meter, and the one with the lowest conductivity of 19 millisiemens per meter. Then zone 3, and in this zone, you're getting intermediate elevation, about like 2.1, average of 2.1 meter, and low conductivity of 40 millisiemens per meter. And zone 4, which is you're getting lower elevation of 1.3 meter and intermediate conductivity. If you're comparing those, as you can see, zone 4 and zone 1 are very similar in elevation, but a little bit different in conductivity. And this is a comparison when it comes to the lateral variation in conductivity and elevation. But how about if we compare those relationships for developed areas and undeveloped areas? So this table is listing the relationship between conductivity and elevation over each zone, but in both areas. So over developed areas, this area here is the developed areas where you're seeing profile 4 and 5 and 6 and 7, and we're comparing this area to undeveloped areas, which is mainly profile 8. So in zone 1, in the undeveloped areas, we're having moderate conductivity and lower elevation. But when it comes to developed areas, zone 1, which is the beach area, the conductivity started to increase. We're seeing higher conductivity in the beach area in developed areas compared to undeveloped areas, and elevation stays the same. Zone 2 is business as usual. It stays the same, lower conductivity and higher elevation in both developed areas and undeveloped areas. By the way, zone 2 is the dune zone here. Now, zone 3 and zone 4 are very interesting, where we're seeing in undeveloped areas lower conductivity in both and moderate elevation. But in developed areas, we're seeing very high conductivity and lower elevation. Okay, so in this central part of the island, we're seeing the majority of the development or the majority of the anthropogenic effects mainly concentrated over this central part of the island here, with also some concentration over the zone 1, which is the beach zone. Now, I'm walking you through each of those profiles one by one, where I'm showing you the spectral signature for both parameters, for the conductivity and the elevation. So this is the location map again here in your right-hand side, and we're starting with the profile BV8, which is pristine area. Think about this as your baseline. This is undeveloped areas, pristine areas, and this profile again is color-coded. Cold colors or blue colors are low conductivity, and warm colors, high colors are higher conductivity. And this profile extends from the Gulf of Mexico to like almost the central part of the island. And this sketch here, or this graph, shows the relationship, the spectral relationship between those parameters. I'm displaying the conductivity in red color here, and in your left-hand side, you will see the conductivity in millisiemens per meter, going from 0 to 400. And in your right-hand side, you're seeing the y-axis displaying the elevation in black color, and the elevation graph is shown in black color here. So I'm showing two main graphs: the elevation graph in black, and the conductivity graph in red. And in this graph, I'm also displaying zones. So zone 1, which is light blue; zone 2, the 4 dune zone, which is yellow color; then zone 3, orange color, and light green color, which is zone 4. Now, I'm investigating each of those zones one by one, and I'm trying to explain why we're seeing what we're seeing when it comes to those relationships between the elevation and conductivity. So for zone 1 here, you're seeing a little bit moderate conductivity up to 148 millisiemens per meter, and lower elevation, which is 1.6 meter. And this kind of makes sense because you're close to saline water from the Gulf of Mexico. So you're close to high tide effects, you're close to storm surge, and that's why you're getting higher conductivity. And also makes sense when it comes to elevation, because the fact that you have the back and forth movement of those types of storms and tides effects, you start to level up this zone, so you're getting like lower elevation. So this is very straightforward zone when it comes to relationship between conductivity and elevation. Now, zone 2, which is a dune zone, what you're saying is you're seeing lower conductivity, 19 millisiemens per meter, and higher elevation, which is 4.5 meter, which is actually the highest elevation. And to explain the lower conductivity for this, this is the higher dune by default. You're away from the storm effect, you're away from the tide, and you're expecting to have a little bit deeper groundwater level in this area. And you're expecting to have also infiltration from fresh precipitation. And you're also, since you have deeper groundwater level, you're expecting to have dry soil in this area. That's why all of those factors combined contribute to why you're getting lower conductivity in this area. But why also you're getting higher elevation? Because we think that the freshwater dependent vegetation, or vegetation growth here in this area, the vegetation is acting as a stabilizing material. So the vegetation roots system is actually binding those soil materials together and makes them more resilient when it comes to the storms and storm effects and the flooding effects. So mainly vegetation growth is kind of responsible for stabilizing this zone, this poor dune field, when it comes to higher elevation. Now, moving to zone 3 and 4, you're getting moderate elevation. For zone 3, you're getting 2.1 meter. For zone 4, you're getting 1.3 meter, and lower conductivity. What I would like you to remember is this figure here, specifically in zone 4, where you're seeing your elevation is low and your conductivity is low, or kind of moderate elevation and your conductivity is low. Then I will take you and move to the northern part of the island, where right now we're looking at profile 2. Profile 2 is the northern part of the island. And again, same color codes for conductivity. But if you look at zone 4, here in this area, you're seeing very high conductivity when it comes to zone 4. Now, zone 1, you're getting a little bit higher conductivity compared to the pristine area. And zone 2 and 3, business as usual. There is no changes, not significant changes between this profile and between the pristine area. But we're seeing very significant changes when it comes to conductivity for zone 4. And we attribute this mainly to the exposure of this portion of the profile to the hypersaline water of Laguna Madre. Laguna Madre salinity is over, I would think, over 50 BBT compared to the Gulf of Mexico, which is salinity of, I think, 35 BBT. So it's this Laguna Madre water body is very hypersaline, and that's why we're expecting this contributes mainly to higher conductivity. Now, moving towards the development areas, and this is profile number 3, and we're speaking here about development. We're think about this as dredging canals. Texas has a lot of dredging canals. Baker Channel is one of them that connects Gulf of Mexico to Laguna Madre. Okay, so in profile number 3, you're getting very interesting results when it comes to zone 1, because the conductivity in zone 1 is very high, it could reach up to 400 millisiemens per meter, compared to less than like 150 in the pristine area. But not only zone 1, you're also getting very high conductivity when it comes to zone 4. And we attribute the higher conductivity for zone 1 to the fact that these measurements were collected very close to those dredging channels. And this area, think about this area as you have saline water from the channel that's connect both water bodies. And also we have saline water from the Gulf. So everything here, like think about this environment as like more saline environment. Now, when it comes to zone 4, think about zone 4 as those types of canals and water housing development canals and dredging canals are actually disturbing the long path discharge pattern of groundwater flow. So you're actually cutting the groundwater flow, discharge flow path, you're cutting them more short. That's why you're ending up having more shallower groundwater level in this area. And with shallow groundwater, you're expecting your grains and your soil not to be that cohesive when it comes to other areas. But also shallower groundwater in this area is also affecting the vegetation growth. So we're not seeing as much vegetation that used to hold the dune tight compared to zone 2, for example. So it's affecting water level, so you're getting more water close to the surface, and it's also affecting vegetation. And most importantly, those developments usually introduce some of impervious materials, and those impervious materials tend to enhance runoff at the expense of infiltration, and that's why we're ending up having what we call evaporation bonds. So those are evaporation bonds close to those areas, close to areas where we've collected data over zone 4. So all of those parameters combined contribute to why we're having higher conductivity in the development area over zone 4. Now, moving to profile number 4, which is again very similar story over zone 4, close to housing development canals that connects Gulf of Mexico to Laguna Madre, and also dredging canals. You're getting very high conductivity that could reach up to 400 millisiemens per meter. And that's mainly attributed to the fact that your groundwater level is started to be shallower, and you started to develop evaporation bonds, and also your vegetation is less resilient here, since you're producing more saline water. You think about your groundwater as more of saline water here in this area. And again, this is zone 4 conductivity. So conclusion based on this, we found very inverse relationship between terrain conductivity and elevation based on EM31 results. Zone 1, which is the beach, has the highest conductivity and the lowest elevation. Makes sense because it's close to the tides and the storm surge. That's why we're getting higher conductivity. Zone 2, the 4 dune zone, has the highest elevation and the lowest conductivity. And this lowest conductivity is mainly attributed to the fact that your groundwater level is deeper, and you have more of dry soil, and you're also exposed to precipitation from freshwater. You're exposed to a kind of fresh precipitation in this area. We've seen the human development affecting both zone 3 and zone 4, and contributing to increase in conductivity and reduction in elevation. And we think that those development and anthropogenic activities modified the hydrogeologic patterns. They actually cut the discharge patterns short. That's why we ended up having more shallower saline groundwater close to the surface. And they introduces new materials, and also they altered the vegetation and the soil composition. And we think that the interaction between the surface and subsurface condition could help us try to develop practice that makes us makes the coastal communities more resilient to those types of storm and hurricanes. In the next few slides, I'm sharing with you our results for ongoing work with a TEM dataset. And again, we're still working on those results. So our results are very preliminary at this stage. This is inversion results for one of the stations. It's located here in this profile. And you're seeing the resistivity decay here with time. And also you're seeing our inversion solution. And we ended up using 5 layers for the model layer. And our geologic layers, we generated fresh water, mixing zone of brackish water, freshwater zone, and saline or clay zone. So those are the three main layers that we'll talk about. And in fact, actually, I will focus only on the freshwater zone here. I'm trying to compare this freshwater zone over those profiles to see how the development is affecting the freshwater lens in the island. And also we're seeing if there is a correlation between the freshwater lens and if there is a correlation between the freshwater lens and the elevation. So this is profile BV11. Think about this. It's the same profile, same location for BV8 when it comes to the frequency domain electromagnetic. This profile is very pristine profile, very pristine area. It covers the entire island from the Gulf side to the Laguna Madre side. And this is a inversion result. This profile covers a little bit over 2 kilometers. And what we did is we assigned threshold of 8 ohm meter to designate the freshwater lens. And this is how the freshwater lens look like. And this is again any resistivity greater than 8 ohm meters, and represented as a freshwater lens. Then we compared the freshwater lens with the elevation. And as you can see, away from the dune field, think about this as like this area here is your dune field. So away from the dune field, over the central part of the island, where your elevation is high, you're getting high elevation, you're seeing the maximum thickness of your freshwater lens. The maximum thickness of the freshwater lens could reach up to almost 18 meters in this area, in the central part of the island, where you're seeing a little bit higher dune elevation and maximum thickness of the freshwater lens in this central part of the island. Now, if you're moving away from the central part of the island, where you have lower elevation here in this area, think about this area, this is lower elevation. You're seeing kind of a reduction in the freshwater lens here, in the thickness of the freshwater lens. So to some extent, we're seeing inverse relationship between the elevation and the thickness of the freshwater lens. Not only the thickness of the freshwater lens, we're also seeing the spatial or the lateral extent of the freshwater lens. Think about this profile in the pristine area here. Your freshwater lens is almost covering your entire island with variable thickness, ranging from like 5 to almost like 5 meters to almost like 2 to 3 meters here in this part of the island. But if you move to other areas, like the developed areas, this is profile BV4, I should say. This profile here, again, this is the inversion result for this profile. And again, this is a freshwater lens in this profile. And this is the elevation. So again, away from the dune field and from this specific dune feature that we've seen mainly in this profile, you're seeing the lateral extent of the dune started to decrease. So moving from 2100 lateral extent here over this profile, over the pristine area, to almost 500 meter extent for the freshwater lens over this development. So we think that the development affected the lateral extent of the freshwater lens, not only the lateral extent, but also the vertical extent, where the maximum depth of the freshwater lens here that we're getting is 12 meters, compared to 18 meters, the maximum thickness from the area that is undeveloped areas, the pristine area here. So so far we're seeing the development is reducing the spatial extent, but also is not only reducing the spatial extent, but also reducing the vertical extent of the freshwater lens. So what I'm displaying now is I'm walking you through this, where I'm displaying the elevation profile again in black color, and in your right-hand side, you're seeing the elevation in meters. And in red colors, you're seeing the dash profile here. In red color, what you're seeing is a thickness of the freshwater lens. And in your left-hand side, you're seeing the thickness in meter. And I'm walking you through the entire island from the undeveloped areas, profile BV11, to all the way to the developed area. So I'm showing you the spatial variability in both the relationship between the freshwater lens vertical extent and lateral extent, and also the dune elevation in this area. So in the first profile in BV8, you're getting the maximum extent, the maximum lateral extent, a little bit over 2 kilometers of the freshwater lens, covering from this side of the island, from this side of the island to the other side of the island. So almost everywhere you will find a freshwater with a variable thickness here in this area. Now, moving to profile 1, which is this profile here, in the very north part of the island, profile 1, very north part of the island. What you're seeing is, again, same graph, relationship between thickness of the freshwater lens and elevation. But what we're seeing in the profile 1 is you're seeing reduction in the lateral extent of the freshwater lens. So compared to profile in the pristine area here, where you almost drill everywhere, you will see a freshwater lens. In profile 1, that's not the case, because you're only getting 800 meters of lateral extent when it comes to the freshwater lens. Moreover, in profile 2, you start to lose more of your lateral extent of your freshwater lens, or you're only getting 650 meters of the lateral extent for the freshwater lens. But not only this, you're also vertical extent, which is the maximum thickness, also decreasing. Now, in profile 4, which is very interesting, very in the central part of the developed area, you only have 500 meters of the lateral extent of the freshwater lens. But not only this profile tells you that in central parts of the island, somewhere you could drill and you're not getting a freshwater lens. So the development in these areas affected areas where you can find freshwater, where you cannot find freshwater. In profile number 4, in this profile, in this part of the profile number 4, you're not going to be able to find freshwater in this area. And this is mainly because of the development. So based on those relationships, we found that the development is affecting both the vertical extent of the freshwater lens and also the lateral extent of the freshwater lens, and also controlling relationship between elevation and those two parameters. So in conclusion for this part, we found inverse relationship between elevation as well as thickness and lateral extent of the freshwater lens. In undeveloped areas, the freshwater lens is wide, thick, and has the maximum thickness. It could reach up to 18 meters in the central part of the island. But also, the maximum thickness is centered over the central part of the island, compared to the developed areas where the freshwater lens is narrow and thin, and the maximum thickness is more shifted towards the foredune field. So I think I forgot to mention this where you look here at this profile, where you're seeing the maximum thickness of the freshwater lens, and instead of centered over the central part of the island, it's shifted. It's shifted toward the foredune field. So you think about the development is actually pushing the maximum thickness, or the freshwater, the development is pushing the freshwater from this side, from the development side towards the Gulf. So you're having like two main forces, the Gulf, the push from the Gulf, and also from the development areas. So the development in the development areas, the freshwater lens is very narrow and very thin, and the maximum thickness is shifted towards the foredune field. And again, we think that this research emphasizes the significant roles between anthropogenic factors and how those anthropogenic factors affecting the hydrogeologic conditions of barrier island systems. And results of this study could provide insights for coastal management and conservation efforts. Sina, I just need like 5 more minutes for something which is related to this, if you don't mind. And I would like to share, because this is very exciting, and I'd like to share it with the community so everybody can get the benefit of this. I would like to share this, our kind of recent experience of using geophysics test site in this coastal areas. We have a geophysics test site mainly dedicated to the coastal area. So probably the first one that is in the coastal area, and the first one here in coastal Texas. Our test site, we used it mainly for research and teaching purpose. It's a 50-meter by 50-meter site, and includes subsurface objects that kind of simulate real-life situations. We have plastic drums, steel drums, and we have steel pipes, and also we have wall covers distributed over 7 rows. This map here shows the rows. The first row here are steel drums. Those are distributed in vertical position, horizontal position, inclined position. Then the third row, you have also steel drums. Some of them is like double drums running parallel, double drums running vertical, and also triple drums. And those are some images for those steel drums here. And the second row has the wall covers. And we have, this is the wall covers here. Those wall covers are distributed at different depths, ranging between 0.5 meter to almost 3 meters. Then row number 3 and row number 4, we have plastic drums. Some of those drums are horizontal, some of them are vertical, some of them are empty, some of them are filled with fresh water, some of them are filled with saline water. Then the last 2 rows, we have steel drums. Not steel drums, I'm sorry, steel pipes. And those pipes were distributed either horizontal or vertical, and some of them running parallel to each other. So that image here shows the steel pipes running parallel to each other. And I have other images, I don't think I have it here, but that shows pipes in vertical position, where they were installed in vertical position. This table shows location and attitude of each object, and the depth for those objects is ranging between 0.5 meter to 3 meters. So and also those objects were distributed in a way that some of them are horizontal, some of them are vertical, and they're also distributed in a way that, for example, for plastic drums, some of them are empty, some of them are filled with fluids. This is very rough results when it comes to magnetic field. This data is collected by top sensor for the G858 geometrics magnetometer, and shows also anomalies over drums and pipes. And this is bottom sensor, again shows kind of explicit anomalies over drums and pipes. We also use the site for teaching, where we collect ground penetrating radar data over using different antennas. We also collect magnetic data. This is our G8 geometrics system, G858 magnetometer system. We've collected gravity data in this site and other areas as well. And seismic data. This is a recent picture for a class running right now. And those are like my current students attending my geophysics class and collecting during our last collection of seismic refraction data over this test site. And we've documented this site in this article here, and be more than welcome to send me an email. I'll share it with you, or you can find it yourself over the leading edge, I think, the leading edge website. In conclusion, we found those sites are very beneficial when it comes to teaching. Students love to go outside and collect field data. I would advise everyone to get use of them. Those sites are, you guys just like need to coordinate with me if you would like to use them for any purpose, for like any research or like teaching purpose. You're then more than welcome to use them for free at no charge. Finally, I would like to acknowledge funding agency. Corpus Christi Geological Society helped us in constructing the geophysical test site. NOAA and Texas General Land Office funded our work when it comes to relationship between subsurface conditions and geomorphology. And we thank you to Padre Island National Seashore for granting us research permit that enable us to do this work. And thank you everyone for joining today and being listening to this. And I will be happy to take any questions.
Thank you very much, Mohammed. That was a very huge work you guys have done, and the end part is really interesting for me as a professor to use like a dedicated site to teach and do some research for students. I, like you, also find it that really rewarding for myself, but also for the students who go out and do field work. They kind of get a hold of what geophysics is capable of doing, rather than just telling them. The word becomes less scary. You know,
yeah, exactly. And I think based on based on my experience, I think they love to go outside. Students love to go outside no matter what. So they're more appealing to go outside and collect data, and they share those experience. And we found it's kind of very helpful when it comes to teaching concepts. And also, instead of just like displaying those types of anomalies in like in a textbook or even like in like a graph or map, you're seeing them, collecting the data and touching the data yourself has a completely different feeling.
Totally agree. So we have time for questions. There's only one question from me in the Q&A, so I'll let that for the last part. We have two people raise their hands. First one is Ahmed Ali. I'm going to, I think you can unmute yourself, or if you can't, I can do it.
Yes, you can hear me?
Yes, we can hear you.
Thank you, Dr. Muhammad, for your beneficial presentation. Firstly, my name is Ahmed Mahmoud, Associate Researcher at Nariag, Egypt. I have like some questions and some inquiries. Firstly, in case of measurements of TEM, okay, why aren't you use ERT?
That's a very good point. We're not allowed to. We're measuring those measurements over national seashore. So our research permit is not allowing us to collect whatever we want at whatever location we want. ERT is very, I think, will produce very good results, but we're not allowed to collect whatever data over the entire island because it's a national seashore. It's a protected areas, so we're not allowed to get whatever we want when it comes to this site.
Yes, but this will be easier, and you can make 2D, 3D slices. I think it will be like good, and you can use it instead of frequency and time domain electromagnetic. I think because this like ART will be less noisy and better in quality of data, I think. Okay, in case of frequency domain electromagnetic, you mentioned some slices or over profile. These slices at which depths, please?
This is kind of the integrated depth from the equipment. So the integrated depth. Yeah. So because the depth is function of the distance between the receiver and the transmitter, and since we have constant distance between receiver and transmitter at 3.66 meters, so we're integrating everything over. Think about the first 5 meters. So think about.
But you mentioned. Yes. You mentioned in time domain in shallower depths, I think till 15 or something meter. But you didn't mention anything regarding fresh water in case of frequency domain at shallower depths. I know it's like till 6 meters or something, but you didn't mention anything regarding fresh water.
I mean, I think I skipped it. However, we found those in profile BV8 in the pristine area. If you remember, we said zone 3 and zone 4 has like lower conductivity. And I think I had it in one of my pictures that in this area you have more fresh water in this area. That's why you're getting lower electric conductivity compared to other zones. So in the undeveloped part on the pristine area over zone 3 and 4, which is the central part of the island, we have higher conductivity from the EM31 frequency domain. That's mainly attributed to the fact that we have freshwater lens. And actually, we've seen it. We've seen the freshwater lens using the time domain results.
Yes, I think it will be more beneficial to focus on fresh water because, you know, something about saltwater intrusion. So
Mhm.
maybe you can, and this will be easier during ERT to see like the contact between saltwater from the Gulf and fresh water, and this may be another study. Also, you didn't mention anything about the geology or lithology or correlation between geophysics, maybe boreholes or something to validate in case of higher elevation or lower to validate this geophysics, I think.
We did. I think I mentioned this at the beginning, probably roughly. It's kind of very straightforward. What we're seeing is shore face sediments and washover sediments and shore face sediments. Those are like mainly sand materials overlaying Pleistocene sediments. And Pleistocene sediments is mainly mud here. So we're having like 10 to like 20 meters of sand, shore face sediments, and washover sediments over Pleistocene sediments of mud. And we correlated actually part of the distribution of the TIM stations is one of them were collected close to a borehole drilled in this area.
Yes.
Thank you very much.
Yes, thank you very much for
Thank you.
your answering my question and for your beneficial presentation. Thank you.
I'll ask my question one. One of my questions was exactly the same thing, that the depth of those electroconductivity map, which you answered already. But the other question is the groundwater table elevation. Does it also change with the topography, or is it just basically kind of flat in there?
Over areas with, I think Ramadan did this in his last measurement. He measures the groundwater level, and it's less than, groundwater level is less than half a meter. So it's very, very shallow. The groundwater level is very shallow in the central part of the island. Definitely, when you have like higher dune, you would expect. We haven't measured it over the dune field. We're not allowed to touch the dune field. It's protected areas. But you would probably expecting a little bit of kind of a following the topography a little bit to some extent. But over the central part of the island, the groundwater level is less than half a meter, like 0.3, 0.4, something like that, I think.
And the other question I have is that, do you think the reason that the thickness and the lateral extent of the groundwater, freshwater in the developed area is very small, is that because of the overuse of groundwater in that region, or?
I think it's because of the fact that the development canals that they built, they started to introduce another source of saline water. So think about your lens, and instead of that, your lens is extended over large, like land area between two water bodies. Now you smashed it, so you have the Gulf from your east side and the development canal, like which is connecting the Gulf to the Laguna Madre, in your west side. So your groundwater, fresh groundwater lens is more kind of contracted because of the saline water pressure from both sides. That's what we think.
Sounds good. Right, we have another person raised their hand. Unfortunately, I can't read that name. Please just unmute yourself and ask your question.
My name is Aziz Yusuf, and I'm Dr. Ahmed's student. So,
cool.
I have a quick question concerning the morphology of the study area. So, as far as I know Barrier Island changes over time. I mean, the morphology. So, I want to know if the morphology can actually affect the geophysical signal. Say, for example, if you carry out the same survey in the next 5 years, you're likely to have this kind of result that you just present. And secondly, I don't know if it skipped my mind, or probably you didn't mention it. Yeah, you said for the zone 3 for profile 1 that the Laguna Madre salinity affected the conductivity. So I want to know, because of the high elevation in zone 2, I think, does the high elevation have any effect on the third zone? I don't know if you mentioned it, but I just want to know if I think.
Sure. Thank you, Yusuf, for that.
And thank
question.
you again for the lecture. Yeah.
Sure. Thank you for the question. I think your first question is, if we're repeating this exercise 5 years from today, are we expecting different signals? I think yes. This is a very dynamic system here. And think about this. Electroconductivity is function of lithology and also fluid contents. So we're not expecting much variation over 5 years in lithology, but definitely we're expecting very large variation when it comes to fluid contents. This is very active system when it comes to fluid contents. You're expecting your groundwater system to respond very rapidly to the tides and the hurricanes and sea level rise. So since those are active system, are dynamic system, you're also expecting your groundwater lens to changing actively to those. So to answer your question, we're expecting changes if we're repeating the exercise again over 5 years from today. Now, for your second question, if I remember correctly, I think you refer to profile number 2 or 3, or profile number 2. I think this profile, the zone 4 of this profile was very close to Laguna Madre, and that's why we're getting higher conductivity, and we attribute this to the fact that higher conductivity compared to zone 1, because Laguna Madre is hypersaline system compared to the Gulf. So we're getting very large difference in salinity between the two systems. That's why we're kind of attributing the higher conductivity for zone 4 to this feature here. Hopefully I answered your both questions.
All right. Thank you, sir.
Great. Thank you very much. So I think we're running out of time. There are a few questions in the chat, so I'll leave them for people to ask you over Slack. So if you are not part of our Slack group, please email Laurie, which I just put the email in the chat, which is ns@scg.org, and she'll invite you to join the Slack group, and then you can ask your question directly from Mohammed over there regarding this presentation, or even if you have any other questions from the community. We are hoping that this Slack is going to help us to kind of communicate and talk about everything. Thank you very much, Mohammed. This was a great talk. I really enjoyed it.
Thank you much, Sina. Thank you. Appreciate it. Thank you.